So let us continue the topic. The last part we studied up to binary to decimal conversion, and now we are moving with decimal to octal conversion. So what is the procedure? Divide the given decimal number by 8, note the quotient and the remainder. Repeat step 1 and 2 until the quotient becomes 0. Until the quotient becomes 0. The first remainder will be LSB and the last remainder will be MSB. Equivalent octal number is then written from left to right, that is MSB to LSB. For example, 459 base 10. So we have to divide this number from 8. So here 8, 57. 57 is the quotient, right? See, now here if I say 8 multiplied by 57 means 456. Remainder is 3, right? And then here 57 divided by 8. The quotient what we get, that should be again divided by 8. So 8 sevens are 56. So 57 minus 56 is remainder is 1. And here quotient is 7 and it has to be divided by 8. Direct division not possible. So here remainder will be 7. The same quotient will be written as a remainder. So 7 is the MSB and the first remainder what we got now, it is LSB. Hence 459 decimal number, its equivalent octal number is 713, 713 base 8, right? So like here in the decimal to binary conversion, how we used to divide the decimal number by 2, no? The same process, decimal to octal conversion means divided by 8. Now reverse is octal to decimal conversion means we have to do multiplied by 8, right? See, the number to be converted is 234.56. It is in octal number. It's octal number, where if you want to convert this number to a decimal notation, then what you have to do? Every digit has to be multiplied by 8. And before the decimal point, whatever we have, it is integer part, and this is fraction part or decimal part. So before the decimal point, whatever the digits are there, 2, 3, 4 are there, from the right side, give the powers to the 8 from 0 in the increasing order. See, 4 into 8 raised to 0, 3 into 8 raised to 1, 2 into 8 raised to 2. After the decimal point, whatever the digits we have, those digits power should be given in negative. That is, after point we have 5 first, so 5 into 8 to the power of minus 1, 6 into 8 to the power of minus 2. So it continues. So now here we have weights 8 raised to 2, then digit is what? 2. 8 raised to 1, digit is 3. So 8 raised to 0, digit is 4. 8 raised to minus 1, digit is 5. 8 raised to minus 2, digit is 6. 8 raised to 2 means 8 into 8. 8 8 is 64. 8 raised to 1 is 8. 8 raised to 0 is 1. 8 raised to minus 1 is it is 0.125. 8 raised to minus 2 is 0.01325. So now 2 64s are plus 8 3s are plus. These all have to be multiplied. Digits and values have to be multiplied to get the final answer. Hence 234.56 octal number, it is equivalent to 156.71875 decimal number. And after that, we have decimal to hexadecimal number. See, whenever there is a decimal to some numbering system, decimal to binary means divided by 2. Go on recording the quotient and the remainder until quotient becomes 0, it should be repeated. Decimal to octal means divided by 8. Decimal to hexadecimal means divided by 16. When it is reverse, like binary to decimal multiplied by 2 and giving the powers. Similarly, binary to decimal it was. Then octal to decimal means multiplied by 8. Then here the hexadecimal to decimal means it is multiplied by 16. Right? This procedure only you have to use. See, now here divide the given number by 16. Note the quotient and remainder. Repeat steps 1 and 2 until the quotient becomes 0. The first remainder is LSB and the last remainder is MSB. So while writing, the hexadecimal number is written from left to right, that is MSB to LSB, right? So 559 is there. 1634 right? So in the calculator you can see 16 multiplied by 34 means 544 minus 559 means it is 15 is the remainder, right? So I did 16 into 34, 544. 559 minus 544 means 15 is the remainder. 16 2s are 32. 34 minus 2 is 2. Quotient is 2 and remainder is 2. Whenever there is a single digit, you will get the same digit as a remainder because 2 cannot be divided by 16. So here 2 is the MSB, 15 is the LSB. But 15 means what in the hexadecimal it is? It is F, letter F. So 559 decimal number equal to 22F, 22F base 16. Now it is reverse process. Hexadecimal to decimal means multiplied by 16. 5AF point D 16, that means what? Hexadecimal number. 5 into 16 plus A into 16 raised to 1 plus F into 16 raised to 0 plus D into 16 raised to minus 1 because it is a decimal value. So here the powers are given 16 raised to 0, 16 raised to 1, 16 raised to 2. So same as like earlier previous methods what we have done. So 16 raised to 2 means 256. 16 raised to 1 means 16. 16 raised to 0 means 1. 16 raised to minus 1 means 0.0625. So now it is A means 10, right? So here 256 into 5 you have to do. Then 16 into 10 because A means what? 10. F means 15. 1 into 15, right? Then 0.0625 into 13, right? 13. If you multiply all these values, you will get the answer 1455.8125 base 10. Now we have, see, now we did what we did. See, decimal to octal, octal to decimal, decimal to hexadecimal, hexadecimal to decimal. Now it is binary to octal, right? Binary to octal, how to convert. This procedure will be different from the previous method. Let's check out what is the difference between the previous methods and this method. Means decimal to octal how it was, but binary to octal how it is going to be, so that we have to see. See, in the given binary number, the binary digits are grouped into groups of 3 bits starting from the binary point and convert each group into its equivalent octal number. The important point, the binary digits are grouped into groups of 3 digits starting from the binary point and convert each group into its equivalent octal number. For whole number, right, it may be necessary to add 0 as the MSB. Similarly, when representing fractions, it may be necessary to add a trailing 0 in the LSB to complete the group of 3 bits, right? So here you see adding a leading 0 as the MSB into the whole number, and adding a 0 trailing, trailing 0 as the LSB into the fractional binary number does not change the value of the number. See, if you are adding 0 in the beginning and 0 at the ending, the fraction doesn't make any change in the value. Let us consider 1 0 1 0 triple 1 is there. So what do? You group them into a equivalent 3 numbers. See, first we have single digit, and 0 1 0 is one group, and triple 1 is another group. So this 1 means remain 1 only. 0 1 0. In the octal number, what happens is 0 0 0 is 0. 0 0 1. 0 1 0. 0 1 1. 1 0 0. 1 0 1. 1 1 0. 1 1 1. So these are the, here I'll show you, when you write octal numbers up to 7, these are the octal numbers 0 to 7. Its equivalent binary digit is 0 0 0, 0 0 1, and 0 0 1 1, and then fourth number. The 3 means actually it is fourth number, no? 1 0 0, 1 0 1, 1 1 0, then 1, this is 7 actually, 1 1 1, right? So that means for the 1 it will be 1 only, for 2 it will be 0 1 0, right? So that means this is 0 1 0, this is 0 1 1, this is 1 0 0, this is 1 0 1, right? This is 1 1 0, and this is 1 1 1, like this. This is the perfect table for octal numbers equivalent binary digit. So based on that, first digit 1 means 1, 0 1 0 means it is 2, triple 1 means 7. That means here binary to octal conversion. So 1 0 1 0 1 1 1 base 2 is equivalent to 127 8 base 8, right? It's equivalent to this octal number. See, now there is a fraction number here, right? 1 1 0 is one group, 1 1 1 1 is another group, 1 1 0 means 6, 1 1 means 7. You need to remember this set, then only you can handle this conversion, right? So hence 0.110111 base 2 is equivalent to 0.67 base 8, that is octal equivalent. Octal to binary conversion. Octal to binary conversion. So reverse process it is, right? The application of total numbers, the application of octal numbers is to represent binary numbers as it is easier to read large numbers in octal form than in the binary form. Each octal digit is represented by 3-bit binary number as in the table. So this is just now what we have seen. This table is very important, right? You need to remember all these things so that binary to octal, octal to binary conversion will be easy for you, right? So now the question is octal to binary conversion. See, 456 base 8, it's octal number. Let's see how to convert it to its binary equivalent. 4 means 100, 5 means 101, 6 means 110. So now 100, 101, 110. So simple. But if you remember this table, then this conversion will be easy. If there is a decimal number 73.16, 7 means 111, 3 means 011, 1 means 001, 6 means 110. So simple 11011.001110 base 2, right? The simple way you can convert. Now it is binary to hexadecimal, then hexadecimal to binary. First, let us see binary to hexadecimal. So now here the binary bits are grouped into 4 bits, right? Starting from the binary point and replace each group by hexadecimal digit. For whole numbers, it may be required to add a 0 as the MSB to complete the group of 4 bits. See, to complete a group of 4 bits, suppose when I group those numbers, suppose if I don't get perfect 4 digit, then you can add 10 to the MSB. Similarly, at the right side after the decimal point, if there are no equal number of 4 digits, then you can add 10 to the LSB. That doesn't make any change in the binary number, kindly note. So the table is like this, 0 to 15, you should remember 0 to 15, right? Already up to 7, you know, just you have to add one extra 0. From 8, it will be 1000, right? So 91001. Similarly, it is up to, right? So it is 10, 11, 12, 13, 14, 15, all the things are given. Based on that, if the number, binary number is 1011001 means 1011. See, from the right side, you make the group. From the right side. 1001, 4 digit over. 101 is left out. So add 10 to it. Right. So it is 010 means 5. 1001 means 9. Hence, 1011001 of binary digit is equivalent to 59 of base 16, that is hexadecimal number. If there is a decimal, what you have to do? From the right side, you make from the left side, see 1101. Anyhow, there are equal number of digits. Suppose if there is a whole number, from right side, you make the grouping. Suppose if there is a decimal number, from left to right, you make the grouping. Suppose if you don't get the equal number of 4 digits with that, then at the last, what do? You add 10 to make it equal, right? So 1101 means D, 0111 means 7, hence 0.D716 is the answer. Now, hexadecimal to binary, they'll give you a hexadecimal code. You have to extract from this table for those hexadecimal code what is the equivalent binary number, right? So based on that, see the code number what they have given is CEBA, right? They have said refer the table 3.5. So C stands for 12, E stands for 15, B stands for 11, A stands for 10. So 12 means 1100, 14 means 1110, 11 means 1011, 10 means 1010. So CEBA of hexadecimal 16 base equal to this binary digit. Now similarly, octal to hexadecimal, then hexadecimal to octal we have to see. Steps are write the binary equivalent of each octal digit, then regroup them into 4 bits from right side. This process is very important. From right side with zeros added if necessary in the beginning, MSB. Convert each group into its equivalent hexadecimal digit. So 274 is an octal number. Base 8 they have mentioned it. 2 means 010, 7 means 111, 4 means 100. Whenever there is an octal, only 3 digits will be there. When hexadecimal is there, remember you need to take 4 digits, right? So hence 274 of octal 8 is equal to these binary digits, right? So similarly, group of bits into groups of 4 bits. See, right side I'll take 1101 groups, 1011 one group, and 0 is left in the beginning. 0 is remaining. So 274 of 8 equal to BC of 16 base. Now it is hexadecimal to octal conversion. You see, there are more type of conversion. Do not get confused. Practice more and more problems to in each and every category so that these conversion headings will not confuse you. Otherwise, these all headings looks like little same only. There is a chance of getting confusion. So practice more and more with a different example. One time with the whole number, another time with the number with decimal. Both options you have to try. Write the binary equivalent of each hexadecimal digit as per the table given above. Regroup them into 3 bits because octal is there, right? From the right side with zeros added if necessary, convert each group into octal equivalent. See the example what they have given is FADE base 16. It's a hexadecimal number. F stands for 15, A stands for 10, D stands for 13, E stands for 14. Their equivalent binary numbers are this. So fade F, all the letter codes have been written here. And after that, right, after that, see hexadecimal to octal they have said. That is why first you convert hexadecimal to binary first. After that, once when you get the binary format of the hexadecimal number, from the right side, you group 3 digits into each group and see if 0 is required extra or what, right? See 110 is one group, you can see here. And after that 011 is third digit group. After that again 011, this is another 3 digit group. After that 101 is another 3 digit group. 111 is another 3 digit group. Only one digit is left out, no? To make it 3 digit group, add 2 zeros, no problem. Then you find out the octal number of these each and every group. After that, fade of 16 equal to FADE of base 16 equal to 175,336 octal base 8, right? Like this, you have to convert. See, direct conversion is not possible from hexadecimal to octal. Hexadecimal to binary first. So you get 4 digit group. In that, from the right side, you group 3 digit. In the left side, if required, add any number of zeros, either single 0 or 2 0. Make it 3 digit group and find out the octal number of each and every 3 digit group number. So that will become the hexadecimal to octal conversion. This conversion is a little different, kindly note. Representation of signed integers. See, signed means what? A number with both positive and negative. That means it may be a positive or negative number, or what is what? Signed number. So some means is required for representing the sign of the number. This is done by adding the leftmost bit to the number called the sign bit. The positive number has a sign bit 0, while the negative sign has a sign bit 1. Hence, it is also called as fixed point representation, right? So a positive number has a sign bit 0, whereas a negative number has a sign bit 1. So a negative sign together can be represented in one of the following ways. Sign and magnitude representation, one's complement representation, two's complement representation. A negative signed integer can be represented in one of the following ways. A negative signed integer representation can be represented by using any one of these 3 ways. First one is sign and magnitude representation. An integer containing a sign bit followed by a magnitude bits are called sign magnitude integer. The MSB is always the sign bit and the remaining bits always stands for magnitude, right? So here an integer containing a sign bit followed by magnitude bits are called sign magnitude integer. Let us see how it's going to be uh, calculated. If in a computer of word size of 1 byte that contains 8 bits, then integer plus 83 and minus 83 is represented in 8-bit sign magnitude representation. How? Plus 83. First what? 83 will be converted to binary, right? Later on what happens? Initially 0 will be placed in the beginning, in the first position, indicating that this is the positive number. Similarly, if there is a negative number, so here in the first place, sign bit, it will be empty for negative number. Then your number will be there 101001. This is the binary equivalent of 83. Binary equivalent of 83. As it is a negative number, it is indicated just by writing a bit 1 in the last position at the right side, right? So still, sorry. So here, 1 minute. Here 10100011 is the binary equivalent of number 83. But in the sign bit here, they have written 1, indicating that it is a negative number. If it is 0 in the sign bit, it is positive number. It is 1 in the negative number in the sign bit, it is a negative number. Like this, it will be understood. Right. Okay. So now here representation of signed integer. That means what? Positive number and negative number, how it will be represented. There are 3 methods for that: sign and magnitude representation, 1's complement representation, 2's complement representation. There are 3 methods. Let us check one by one. Sign and magnitude representation. An integer containing a sign bit followed by magnitude bits are called sign magnitude integer, right? That means what? In the representation, first there will be a 1 bit is reserved for representing sign, whether it is positive or a negative. Next bits, remaining bits are used for representing the value of that number, right? The binary digits of that given value, right? That is called as magnitude. For example, if in a computer of word size of 1 byte, that is 8 bits, right? Word size, it is of how much now? Here 1 byte, for example. That means how many bits? 8 bits. That is why you see down here 8 boxes are created. The number to be represented using sign magnitude is what? Plus 83 and minus 83. They want to show you both positive and negative number, how it will be represented. In these 8 boxes, which represents 8 bits, first bit reserved for sign. That is why you see that with the arrow mark, they have shown you sign bit. And the remaining 7 bits are used for representing your value in the binary format. So now here plus 83 plus means sign bit will be 0. And the remaining 7 bits, what we are saying, this is the binary equivalent of decimal number 83. Similarly, minus 83 means 83's binary equivalent will be same, but sign bit will be what? 1. Sign bit will be 1, right? So where the sign bit will be 1 says that it is a negative number. So 2 raised to 7 equal to 128 numbers can be represented using 7 bits, means you can represent plus or minus 128 range of values with the help of sign bit, sign and magnitude representation. Next method is 1's complement representation. This is the simplest method of representing negative binary numbers. Negative binary number is formed by subtracting the value of each bit in the word from 1. This changes the value of 0, the value of each bit from 0 to 1 and 1 to 0. Let us take an example. Consider the binary number 101000 is the binary number. Let us see in the ones complement representation what it is going to be. So for 101000, you add 1 to every bit. For every bit you add 1. So 1 plus 0. Sorry, subtracting they have said. 1 minus 0 is 1. That is nothing but 0 will be changed to 1 and 1 will be changed to 0. Right. 1 minus 0 is 1. 1 minus 0 is 1. 1 minus 1 is 0. 1 minus 0 is 1. Then 1 minus 1 is 0. This is the ones complement representation of 101000. Right. So we observe that ones complement of binary number is easily obtained by changing all ones to zeros and zeros to 1. That's why this is simplest method. Whereas in the twos complement representation, what you have to do is you have to find out the ones complement of a given binary number and add 1 to it. That will become twos complement representation. Now here ones complement of 10101000 equal to ones complement of 101000 plus 1. So ones complement of 101000 is how much? 01011. That we have done here calculation. That is why directly they have written. Plus 1 means what? Here 01100 it is going to be. Hence 011000 is the twos complement of 101000. Right. So consider a signed integer minus 14 to be stored in an 8-bit register. Then how it is going to be? First thing is what? 8-bit, totally 8 boxes. First bit reserved for sign. It's a minus sign, so sign bit is 1. 14's equivalent binary digit is this, right? And signed ones complement is, suppose if we are representing using ones complement, then what happens? 0, 1, 1, 1. That means zeros will become 1, 1 will become 0. All these 8 bits, you swap it like this, you will get this answer. And sign with 2 means what? First you have to find out the ones complement and adding 1 to it. So then the result is going to be 9, right? So all the modern computers, they operate based on twos complement representation only because of its hardware being simpler, which makes the computer to work faster. So here binary arithmetic is very important, right? For all the digital computers, the fundamental operations are binary addition, subtraction, multiplication, division. Binary addition is the most important one. Based on this, we can do all arithmetic operations. Binary addition, add and 1. There are table given here, add and 1, add and 2. 0 plus 0 is 0, carries 0. 0 plus 1 is 1, carries 0. 1 plus 0 is 1, carries 0. 1 plus 1 is 0, carry 1. Right, the above table adds only 2 bits and gives the sum and carry. If a carry is generated, it should be carried over to the addition of next 2 bits. Similarly, 3-bit addition, right? So here add and 1, add and 2, first one, and previous carry, right? Previous carry plus, wait, first add and 1, add and 2, then previous carry. With by adding these two, what previous carry will come, right? So here 0 plus 0 is previous carry they are saying. Okay, 1 minute. So the following table gives the rules to add two addend bits and carry generated from the addition of previous bits. Here one example is there, 75 and 18 have to be added in binary. So in 75, what they have done is they have taken the bits. So here 64 bits, 8 8s are 64 in 75, right? How much is left out? 75 minus 64 means 9 is left out, right? 64 means, no, not 9, 11 is left out. In that 11, 8 means 1 byte, 8 bits we have taken. In 11, still 3 are there. Then 2, then plus 1 they have taken. So altogether it is going to be, the binary format will be this much. And similarly, 18's binary equivalent will be this. And then, so addend 1, addend 2 will be added and carry will be recorded and the total sum will be this one. Then similarly, binary subtraction. It is performed as the addition of negative binary number. 8 minus 5 may be performed as 8 plus minus 5. Right. 8 is a positive number. Minus 5 is the negative number. Right. So the basic rules are like this. Here instead of carry, borrow will be there. 0, 0, difference will be 0, borrow will be 0. 0, 1, difference will be 1, borrow will be 1. 1, 0, difference will be 1, borrow will be 0. 1, 1, difference will be 0, borrow will be 0. Based on this table only, it will be handled. When we subtract 1 from a 0, it is necessary to borrow 1 from the next left column. That is from the next higher order position. Right. 1 from 0. Necessary to borrow 1 from the left column. Right. That is from the next higher order position. Subtraction 75 and 25. There are two numbers, and here minuend and subtrahend. There are two numbers. Difference will be calculated here. Subtraction using 1's complement. Though subtraction using borrow is straight, the computer does not use this method due to the circuit complication. It does subtraction using complement method, 1's complement, 2's complement, those things. Subtracting a smaller number from a larger number, right? That means minute number is greater than the subtrahend. So find the 1's complement of the subtrahend, right? That means what? Second number. Add this to the minuend, right? Minuend number. Then carry is generated. This carry is called as the end around carry. Add the end around the carry back to the LSB to get final difference. 23 minus 15 is there. Okay. These are the equivalent binary version. And here, what is the subtraction answer? 1's complement. First, you have to find out the 1's complement of this number. Right. So 0 will become 1, 1 will become 0. So it is, this is the thing. And after that, the first number, minuend 10111, that should be, so to calculate end around the carry, here that is 1, which is highlighted here, right? Add end carry to the LSB, that is to the least bit. So final result will be this, that is the difference. Subtracting larger number from a smaller number. In such case, find the 1's complement of subtrahend, add this to the minuend, there will be no carry, recomplement the answer to get the difference, add the end around carry back to the LSB to get the final difference. This is minuend and this is subtrahend, and then first minuend ones complement of the subtrahend. So both will be added. So there is no carry. Therefore, recomplement the answer. 1 0 1 0 0. It will become 0 1 1 0 1 1. Right. Complement means it is reverse. 0 will become 1, 1 will become 0. Subtraction using 2's complement. Subtracting a smaller number from larger number. Minuend is greater than subtrahend. Find the 2's complement of the subtrahend. Add it to the minuend. Carry is generated, discard the carry and the remaining bits give the difference. So here these are the binary equivalent of 17, then 9. Both have to be subtracted. 2's complement of, see they have said find the 2's complement of subtrahend. That means this number's 2's complement, how you will calculate? First find out its 1's complement and add 1 to it. That is 1 0 1 1 0. 01001 equal to 1's complement of 01001 plus 1. So it will be this much. Then you add it to the minuend. So then here this answer will be generated. Carry is generated, which is highlighted here, darkened digit. Discarding the carry, we get 1000. It is equivalent to 8. Similarly, subtracting larger number from the smaller number. That means what? Minuend is less than subtrahend. Find the 2's complement, subtrahend, add it to the minuend. There is no carry, hence take the 2's complement of the answer and place a negative sign in it. Right. So subtract 47 from 26 using 2's complement. 26 minus 47, their equivalent binary numbers are given. And after that, find the 2's complement of the subtrahend. So it's 2's complement is 1's complement plus 1. So the answer is this, and that should be added to the minuend. This answer should be added to the minuend. Answer you get this one, and just add 2's complement of the answer. That is just place a negative sign before the binary digit. That will become minus 21. And after that, computer codes. Computer codes are used for internal representation of data in computers. As computers use binary numbers for internal representation, computer codes use binary coding schemes. Right. Computer codes are used for internal representation of data in the computer. As computer uses binary number system for internal data representation, computer codes use binary coding scheme. In binary coding scheme, every symbol that appear in the data will be represented by a group of bits by using 0 and 1. Thus, computer codes represents various characters, numbers, and control keys that the computer user selects on the keyboard. Some of the commonly used computer codes are binary coded decimal, BCD, extended binary coded decimal interchange code, EBCDIC, American Standard Code for Information Interchange, ASCII, XS3 code. Right. About that, one brief explanation. Introducing these numbering systems. One way of encoding decimal number digit by digit using 4 bits is called BCD code. Two popular 4-bit BCD codes are BCD code or weighted BCD code or 8421 code. It stands for binary coded decimal. It is one of the early computer codes. In this coding system, the bits are given from left to right, the weights 8421 respectively, since these weights are just place values in the binary number system. A decimal digit is encoded as its binary representation. For example, the decimal number 537 is represented in 4-bit, right? 8421 BCD codes as the 537. Its equivalent binary digits are 4-digit codes are like this. And then in a 4-bit BCD code, only 2 raised to 4, 16 configurations are possible, which is insufficient to represent the various characters used by the computer. Hence, 6-bit BCD code was developed by adding two zone positions with which it is possible to represent 2 raised to 6, that is 64 characters. So these are the characters and these are the zones and these are the digits, right? All 26 letters numbers representation they have given 6-digit representation. 4-digit representation is done by BCD code, and in the zone you have to add the code, right? And the XS3 BCD code or XS3 code, in the sense, it's a non-weighted code and is obtained from 8421 BCD code by adding 30011 to it. Decimal number 537 would be represented as like this. In all methods they have shown, 0101 is the binary equivalent of 5. This is binary equivalent of 3, binary equivalent of 7. So decimal digit 8421 BCD code. So after that, what do you have to do? Add 3 to it. That will become XS3 code. So there are 8-bit BCD systems. They are 8-bit. See, it was earlier 4-bit. Then it came to 6-bit. Now it is 8-bit BCD code is called as what? XS3. Here it is. XS3 EBCD IC. So it will give you 256 possible code groups. Right. Zone will be of 4 digit. Digit will be of 4 digits. So totally it will become 8 digits. ASCII American Standard Code for Information Interchange. It's a 8-bit code which is possible to represent 2 raised to 7 equal to 128 characters. First 3 bits are used as zone and the remaining 4 bits are used to indicate the digits. And then ASCII table description, everything they have given here, 0 to 255 ASCII codes will be there. So base is up to 0 to 127. For which ASCII code, what hexadecimal code is there and what symbol is being represented. Yes, this is the completion of third chapter.